Good morning. We're starting class now on the 9th of November, the day after the elections, the day after all the advertising could stop on the media and all the text messages that I've certainly been getting. They've been kind of ridiculous, but politics has moved into the text messaging domain for sure. Well, I haven't done any grading, but I did put up solutions for set number 4 right after they were turned in. I've put out some hints for set number 5, which is now the focal point for your homework side. And it seems like I tweaked something more on the project. That was last week after class. I fixed a bug in that was basically created by the deprecation of PyLab. Remember, we use that magic in the notebooks. We don't use it anymore because it's being deprecated. So when I'm doing the imports, there has to be some other sub-package names put on. And I'm going to demo that here pretty much right at the very beginning, just because I want to get that off my shoulders. It was something that was done that I cleaned up last week. I'll also be probably doing a demo in the lab today and may refer to it even here in class. I'm not really sure. I have that ready to roll though. Before I leave the schedule idea, I just want to review again what is going on with our calendar here. We're on the 9th. Whenever we hit November, things always move rather quickly. We have these 3 weeks of November that end with November 18th being the week before Thanksgiving. And I'm just highlighting that again because that's the day that I'm going to post up the take-home exam, which I've polished up almost 2 weeks ago now, or maybe it was a week ago. I was working on it. So I'll be giving that out. So we'll be racing down through chapter 5, the end of lecture today, and then on the 16th. And then you'll have homework problems to do for that are due on the 18th. And it's especially important that they get turned in a timely fashion, whatever you can get done on them, so I can put up the solutions and they can be available for the take-home. The take-home problems will be all the material since the last exam, and it will cover portions of what's from chapter 5. But hopefully I'll calm you down a little bit about chapter 5. It's kind of the beginning of the down tilt of the lecture material. It's application stuff, and it's kind of gives you a good feeling to know about being able to use all the skills you've been working on. Remember, we started in the time domain, we went to the frequency domain, went to the Z domain, and then we've been in sampling theory and multi-rate sampling, and then I've made the back half of that chapter random variables and random processes, so we can start using quantization noise. And those things are all going to be in that exam. And it's very good material for sure. So I'll leave that behind. If I just speculate all the way down the line, we're in here in December 14th. That is the final exam day, right? As I have it. And I haven't really studied when it's going to take place. I'm going to guess it's going to be something like 10 in the morning, because that's generally what it is for a once-a-week class. It's not at 8 o'clock. Has anybody looked at it? You can believe it though, right? Some classes get shifted by a couple of hours, and I think this one does get shifted. So, and those of you in the lab, there is a lab quiz, but that should be given probably the last week of class. So that will probably be given on the 7th, would be my guess. I'm not giving it, but I'm giving the materials over to Geronth to allow him to give that. And there'll be some modifications to the labs too, the way I see it right now, because the pattern that I saw last year when I ran everything is happening again this year in the lab. Getting behind. I'm not going to eliminate any labs, but I will suggest to him that he eliminate parts of labs, but still doing coverage through the labs. So what our topic is for today, to wrap through this, will be digital signal processing of analog signals, and that's this block diagram we looked at last week. But before I actually go do that, I'm going to clean up, like I said, the Pi audio issue that came up last week. But it also points out a good situation that you have to be mindful of when you're working with Pi audio helper in particular. So that's this guy right here. Just going back up to the top of this. So remember, this is the block diagram for how we're interfacing to the audio subsystem on the computer. In the middle of that is a callback function that allows us to do real-time DSP. And then we have the pink boxes are the widgets that give you controls. And then global variables are used to take variables from the workspace of the notebook and make sure they get inside the callback function. Why? Coding practice says that functions have local scope, right? A function cannot see outside of its box. So even though it's mysterious, it seems to work a lot of the time. I think it's good practice because you're just asking for trouble, and that's what the Python community told me when I first presented this. And that reminds me, if you're wondering more about this, I did write a paper, and it's linked right here in our sidebar. Oops, that's the 3D audio simulator. Well, the 3D audio simulator, which is a very cool project that I just haven't demoed for a while, because you can put headphones on and hear audio spinning. I thought I had it in here.
Oh, it's in the project.
Is it? Yeah, this is the paper, though. If you wanted to read more about Pi Audio Helper and what it brings to the table and what some of the methods are and things available, this was what I wrote to present at the conference that year, and then that I've since been using in the class. I would say it's a one-of-a-kind thing. Nobody else, I don't know if anybody has adopted it like I have since I created it and had help from graduate students working with me. But that's always out there if you want to understand more about what's going on inside Pi Audio. So the first thing I did when I got on my system, because, and this is just a quick review, when you're using Pi Audio, if you change configurations in your system, like today I plug in my little USB audio dongle, and that remaps everything. So I had to restart my notebook after all my devices were plugged in. Remember, if you change configuration after you've started the kernel up, which is what you do in this first cell, then you have to restart it if you've made a device change. And I'd made a device change, so I restarted my kernel, which generally for me is hitting this button right here, which says restart kernel. And then the first thing I do is go down here and see how are my devices in the audio subsystem being mapped. And for me, I want to use the onboard audio subsystem. I don't want to use the external one. Just that was my decision. So I want the Realtek audio, not the USB audio device for the input. So that's 2. I want the speakers and headphone from the Realtek system, which is index 4. If I wanted to go the other way, I would go 1 and 5, but I don't want to do that. Even though I have the interfaces sitting right here, I'd just as soon not do that. So what I had to do then for the example, I'm just going to scroll down to that example now, and that is this pre-made tunable bandpass filter example, which is equivalent to what you do in Lab 5 when you're doing IIR digital filters, except there you're going to write the code in C. So those of you in the lab, this section of the sample notebook here is very important and valuable for reflecting on for Lab 5. It's also in the sample notebook for Lab 5, but it's utilized in here. So the big thing that's utilized in here, and I've run some of this already, is this function right here, simple bandpass filter coefficient design. This is not part of your project, it's just an example, but the ideas here are useful in working parts B and C of problem 5 in the project. They're the same kind of methodologies, same kinds of approaches. So this function just wraps up a design to get the A and B coefficient vectors for this tunable bandpass filter, and that function is going to be called through the callback so that you can on the fly design the filter and use the slider controls that are defined here to tune it. It's a second order bandpass design. It has poles, complex conjugate poles, which set the center frequency of the bandpass filter, and then it has zeros at z is equal to -1 and +1. Once we get into chapter 5, we'll start looking at, we'll look very briefly, but we will cover the idea of geometry and how pole and zero placement can give you a rough idea of what the response is going to be. Because if we're sampling around on the unit circle, and that's our frequency response, remember, is when we sample around on the unit circle, think of the cookie cutter going down there, getting that complex response, laying it flat, and it becomes the magnitude response. As a matter of fact, it's plotted right down there. So you can see at 1,000 hertz, relative to the sampling rate of 44.1, which is used in this example, or no, 8 kilohertz, excuse me. 8 kilohertz is used in this example. That's 1 kilohertz. Actually, if you think about it, that's how many degrees is that pole sitting at? If I said the sampling rate is 8 kilohertz and I set the center frequency at 1 kilohertz, that should be how many degrees? 45, right? Because that would be 1 kilohertz sitting at 90 degrees corresponds to 2. Over there at pi is 4 kilohertz. That's the folding frequency, and it comes around the bottom. 6 kilohertz, and then it starts all over again at 0, which is like 8 kilohertz, just thinking in terms of sampling theory. So the 0 on the unit circle here and here makes sure that the passband is tied down to 0 transmission, and then this creates a peak because there's a pole coming up and it's close to the unit circle. So as you zoom by on the unit circle and see that pole right alongside you that's going up to infinity, right? It's going to stretch this rubbery surface all the way up. I'll be going into more of that view in chapter 5, but that's why we see what's going on here. These two areas are going down to minus infinity, but this is where the peak is. So here in the callback function, again, none of these callbacks take an input. They just have the input turned off, but that's the way Pi Audio Helper is written. It's written for I/O, and if you don't want to use the input, you just simply ignore it when it comes in. So here I'm just using a playback of samples which get created down here from an 8 kilosample per second audio wave file. You use this in problem 5. And then I convert it to a loop object, X loop, and I just create that, and I think what I'm doing here, I started at an offset of 1,000 samples only because there's some silence in there. So when I create the loop, I'm trimming off some of the dead air in the audio file. That's optional. If you didn't put that in, it would still work. It would just be a longer vector, and it would always have at the beginning of the vector a bunch of nothing, right? Just noise. So it trims it down some is what it does. At any rate, that, reading the code now, I grab some samples from that, a frame count's worth of samples, and remember it's a circular buffer, so it just grabs as many as it can, and if it runs past the end, it will come around and start over again. So for me, being a person that grew up with vinyl records, it'd be like the record spinning around in a circle and starting on the data all over again. I scale it by 32.767. This maybe is pushing things a lot, because if this wave file, which can swing between plus and minus 1, pushes up past 32.767, I'm going to get an overflow in the signed arithmetic. So for safety purposes, I could scale this down to say 32K. I'll leave it there for right now. And then I'll add in some noise. So I'm going to take Gaussian noise of the same vector of the same length, and then use the equation for signal to noise ratio that's there in the Jupyter, or that's defined up above, to set a signal to noise ratio, which is basically through the standard deviation of x, which is the input vector, so it's getting the approximate power. Square root of that would be the RMS power, and then I use that to form a signal to noise ratio and then form the noise that I want to add in. So that's what the plus equals is. And then I go off and use the slider controls here for both bandwidth and center frequency to, on the fly, come up with my filter design. So it does that all within the callback. And then I use those coefficients immediately in the filter, L filter, except now I'm using L filter along with zero initial conditions. So I have an array that comes out as a global ZI bandpass filter, and I actually sneak in the definition up here, if I can find it. This is step 2A in what I wrote into the reader for the project. Step 2A does some initialization stuff, and it designs an initial set of filter coefficients, and it also goes ahead and obtains the initial state vector to be used in the bandpass filter. So this little bit in here is intimately tied to down here in the callback, where I already have an initial state to put in there. It's going to be zeros the way I've defined it, but then once it gets up and rolling, when it processes the first record of data, the first frame count length of data, it will return a ZI bandpass filter initial conditions there on the left, which is global, and then the next time I enter this callback, it will be able to put that into the filter as an initial condition. So it forms a contiguous filtering operation. That's really, really important. Real-time DSP and C code, we do the same thing with the state vector, but we're doing this state vector idea, so we can process vector upon vector and have the initial conditions managed for a memory type device, which is the filter. And then it goes out, it gets gain scaled, and down here I can now run it. Down here what I'm doing is creating the DSP IO object. I'm not going to do any capturing. I'm doing one channel only. And like I said before, this is where speech file gets loaded into a loop, X loop, and X loop gets used to call as the input without having to use an actual analog input to just stream it every time it grabs another set of samples contiguously. When you're doing this sort of thing, when you hit and compile this cell, and if you see these two buttons are part of Pi Audio Helper, they're the fundamental control buttons for it, but then this last line brings up your widgets. If you see all this stuff come up, you can go thumbs up, I think I'm good to go. But that doesn't mean it's going to work, and that's what problem I was having last week. So the subtle thing that was happening last week was I didn't have random dot in front of rand n. In the old version of using PyLab, it imported everything from the entire workspace, from the entire NumPy into the workspace. And then they're including any sub, I'm trying to get the right word, not subclasses, but no, I just can't think of the right name right now. It wasn't importing random. So when I was trying to address rand end last week, it was giving me an error, but it wasn't displaying an error, right? Remember that? It didn't. It just was silent, and it looked like it should be running. Well, that's the lesson I want to teach you guys. If you make a mistake in your callback, sometimes it will just do nothing, and you're like, it looks like it should be working. Why isn't it working? So what I had to do to get to the bottom of it is I had to start commenting out some of the lines I wanted to have in here and just get it back to the bare bones, you know, input, which is from my looping class. Will that play through the system? And then I started staring at it some more and commenting and uncommenting and thinking, okay, one of these few lines of code, it's not like an infinite number of lines of code now, right? It looks fairly simple. Something was hosing me up, so then I went off to the side. You know, I grabbed this and put in a different number. I put in like 1024 or something and put a cell right up above here, and I saw, oh, that is not working because of the fact I don't have a path to that submodule. Module was the name I was thinking of, submodule called random. So I went ahead and put random dot in front of it. The rest of problem number 5, the sample code I give you, I changed in the zip package last week. I put random dot in front of it because both 5B and 5C use noise. And so I changed that. If you haven't downloaded a new version of the zip or just want to manually change it, you're going to have to do that. If I just scroll down here, it gets used here. Go down to this one. I also am adding in, maybe I'm not adding in noise in this one. Yeah, I am. I'm adding noise into this one, so I changed it. I don't like subtle errors where you don't get any tactile feedback. I don't think any of us do, right? Why do I have a flat tire? You know, I can't see a nail in my tire. Why did my tire go flat? Have you ever experienced that? A side story was on my walks, I was going past a car that I could see, the wheel was turned out and I could see on the rubber or the tread there was a screw screwed tightly into the tire. And I thought, why isn't this tire going flat? And it went month by month. I never saw anybody come out of the house, so I was going to be friendly and say, hey, do you realize you have a screw in your tire? Because screws have a way of getting in tires, right? Deck screws or other screws that people get thrown on the road. And I finally told him, and he said, thank you. I don't know whether it ever had a problem, but I've had that exact problem happen before, where the screw eventually doesn't form a good seal anymore, and then you do have a flat tire. At any rate, that's kind of what's going on here. So I ran it, and I can now run the code.
Paint the sockets in the wall dull green. The child crawled into the dense grass. Ride, fail where honest.
So this changes the bandwidth of the
Trample
filter,
the spark, else the flames will
and this
spread.
changes the center
The
frequency.
hilt of the sword was carved with fine design. A round hole was drilled through.
Now, why did I
sword.
put in this bandpass filter? Well, when I add in
Showed the
noise,
path he took up the beach. She was waiting at my front door.
the idea here, and it's almost clipping, which is why I probably change it from 32 down to 30K. It's a male voice, so I think, okay, it's going to be lower pitched, so maybe I
The
should
child crawled
center
into
my
the dense
frequency
grass.
down lower,
Ride, fail
and then
where
narrow up
honest
the
men walk.
filter to just include the
Trample
harmonics
the
right
spark,
around
else
the
flames will
speech.
spread. The hilt of the sword was carved with fine design. A round hole was drilled through the front door.
What's the best?
Footprints
I don't know.
led
I get the problem you have here, 5B, is similar, but it's not a bandpass filter. It's trying to figure out what is the best thing for you to make discernibility. I mean, I think it's our hearing process and what's the best.
The child fall into the bed first.
Anybody have an opinion? To me, it sounds better if I center it down at a lower frequency spectrum, because the strong harmonics from that voice are down in there. The bandwidth, that little shuttering is clipping, so it's overloading. This is kind of like how wide a bandwidth do I need, because when our vocal cords vibrate, they produce harmonics. We need a certain number of harmonics to give our voice a full sound, but it lets through more noise. So how could I fix this problem? I could change this to 30,000 or something, but at any rate, sound good? I mean, the idea of what you have to do, and it does indeed work. And you're listening to one of my famous 8 kilohertz samples, which I've used in a lot of different projects. Used to use it in COM 1 all the time too. So it just keeps looping around. What it is, it's a set of audio reference files that is available on the internet, and it's available in all different, well, English speaking only is what I go for, but it's available in male, female, I think child. The ones that I'm the most fond of using is US male, British male, and US female, just for the fun of it, testing different types of voices. Cell phones go through these things. That's how they make sure the vocoder in your cell phone works good for all different types of pitched speakers. So I've got that resolved. I'm now ready to go into this section of the notes. Are there any questions though on the project right now, since I was just doing a project related thing?
Just submission.
Just what?
How would you like it submitted?
All as a PDF again?
Okay, so each separate file print to PDF.
Yeah, that's fine. I mean, I would think you should be able to use that markdown to PDF conversion with the page spaces and that sort of thing. My solutions are in a PDF that consists of 2 parts that I merged together. 1, 2, 3, and 4 is all one big PDF that I created using that markdown in the page separators, remember? And then I have a separate notebook for 5, and I put those in. I created a separate PDF from those, and then I merged the 2 PDFs together using Acrobat. That was my approach. I would like to have one file to grade all the way from top to bottom. Another thing, I guess, now that we're rolling on this, there's too many things to think about. When I reposted the project, I did something else for you too. I added something at the end of this file. So I added, and I went into this also and corrected the random things that I was just talking about. I'm pretty sure I did. Nope, I didn't. I thought I fixed all of these, but I didn't. They're fixed in the notebook though, the sample notebook. But down at the end, after the bibliography, oh, I know what this is. This is the old one.
You have the new one.
Yeah. I'll recall this and see if that fixes it.
No, you clicked on a different link.
Oh, really? I don't remember what I did. I do have a section in the end of this, though. Yeah, it's in between these two. So that's on the web page?
It's on the web page. Go back and you see you clicked past it. You need to click one above it. See above, right?
Oh, that's right. That is the really old, the one from last year. I still don't have rand n fixed in this, but that's not as big a deal. There. So I added these comments in that I promised you. I was working on these at the emergency room last Thursday, actually. So I have those comments in, and this is another thing that I think you need to look at just so you know how I'm grading this. So this shows you the points. This is my grading rubric for this project. Why should you care? Times get tight and you have to call certain shots in your life, what you're going to do and what you can't do. So you have an idea of what things are worth. The Pi Audio projects seem daunting because they involve a lot more stuff coming together, but in the end they're not really all that hard. They go pretty nice and smooth once you get into that, and I've talked about that. Some of that got captured in the video last week. Number 4 is also very nice and smooth. It's the notch filter and doing a transient analysis. I spent some time talking about that up here. So you got some more little comments to read about that. Polyphase decimator is not really too bad. The hardest part is part B. And I spend a fair amount of time talking about that. So you just have to look those over and see what you think. This one is long and tedious, but I gave you a bunch more hints on that one. The first one, you just got to write your code and test it. And I give you the simple idea that you just hand iterate it to see are you getting the right numbers out with the initial conditions, just cranking the difference equation manually. So that's that. I'll maybe add the random dots in front of there when I get a spare moment to want to go off and do that, but you've seen it in class today. So we'll be looking at quantization here pretty soon, but before we do that, I put together some animation in Julia, so we're going to use that first off. So back over here to this, and this comes from the book, a redrawing of what the book had. So we're going to talk about anti-aliasing filters. There's a bonus homework problem on that you can do, pretty straightforward. Sample and hold, which may or may not be present in front of the A to D or embedded into the A to D. So those two may come together. Then the discrete time system we've been dealing with all the way along since chapter 2 of the book. Then the D to A, and then the output of the D to A is followed by a reconstruction filter, HR, and the tilde's on there because this filter is typically compensated in some way, and that's what the bonus problem on this set number 5 is all about, building a compensating filter. So the first discussion is pre-filtering to avoid aliasing. What can we do about that? So we have to generally put some analog filter out in front of the continuous to discrete to limit the bandwidth of what's coming into the sampler. If we don't do that, any signals above fs/2 will fold around and we'll be hearing them, and they're definitely annoying. They're unacceptable, as a matter of fact. So we have to come up with some analog filter design, and what's the best way to do that? This math here is just showing you how the effective response is going to be your digital system cascaded with the anti-aliasing filter, assuming that there's no aliasing. Another side effect is, if you want to model the effect of the aliasing, you would have an additional term that would come through, and that's talked about here briefly. So one of the fundamental ideas of multi-rate sampling is that you can simplify the analog design. So you don't need as high an order of filter, because what's really challenging, I'm going to come back to that. What's really challenging right now is that if the signal is band limited to that triangle, that omega n frequency, then you just have to sample at greater than twice that frequency, and you'll have no aliasing from the desired signal. But as this picture from the book shows you, there's going to be some high frequency noise, maybe some low-level interference or other spectral contents that you don't want getting into your front end of your sampling system. So how can you deal with that? Nominally, if you're not going to do oversampling, and this is your analog spectrum, you have to come along and you have to try to design a filter that will set right in here and be almost ideal. If I can get this to work. Do something like that, just to carve out the desired signal spectrum and try to eliminate the noise, and which would alias, right? The whole idea of the aliasing is you say it's above my hearing range or it's in an area that I don't care about, but when it folds around, it becomes something you do care about. A whistle or some other strange thing will be heard inside the passband if you let things fold around. It might be an adjacent radio signal, in which case then it's going to be jamming your system. It never was jamming your system before you sampled it, but as soon as you sampled it, just aliases down in, and there you go. You've got something you definitely don't want. So an architecture to deal with that, avoiding having to build doing this topic in here, is do that. It becomes expensive to have to put a high order analog filter in. So this talks about doing it with a lower order anti-aliasing filter coming into the continuous to discrete at a higher sampling rate, then building in the digital domain a high frequency cutoff digital filter. Notice pi over m. Where have we seen this before? In the project problem, you have pi over L that you have to put in there for the interpolation filter. If you're upsampling or downsampling, though, remember it's the minimum of the two. That was talked about in the notes. But if you're, in this case, we're downsampling, so we want to protect the downsampling operation from creating aliasing. And in this case, we're just trying to minimize the order of the analog filter and push the higher order sharp cutoff filter into the digital domain. So this picture, like I said from the book, just shows you that if you build a low order analog filter, which is what's sketched out there, it doesn't look like you're able to get rid of too much of the noise, but you can at least protect the input from the aliasing that might happen in this band. If that becomes approximately fs over 2, then you will get some aliasing of the noise, but it's not going to fold into your signal. Actually, it's not fs over 2. It depends on what the sampling rate's going to be. But in this picture, just shows you that some aliasing could be allowed as long as the aliasing was only controlled to this interval, then you'd be okay. But now you can bring the signal down into your system, and this last spectral plot here is just showing you the high order digital filter is now thrown off. The wideband noise that's maybe aliased, that's present, but you're now going to fine tune it with a high order filter and not sweat the details of the high order analog filter. This comes right from the book. Any questions on it? Because I'm now going to show you another sort of a scenario and how the two are related or maybe unrelated. This is just saying if you can do it. You know, one of the things about this is if you can't oversample right up here, if you can't sample at m times the rate that you would need nominally with a high order anti-aliasing filter, you have no choice but to suck it up and have to build the high order anti-aliasing filter. You just don't have a choice. A project that I was on starting last December and through the first part of the next semester, I was helping a company in California that was building a 5G base station for, let's see, I'm trying to remember the acronyms. I don't remember them. The project got canceled, so I quickly erased my brain and don't remember what the name of it was. It's the open standard. Oh, that'll make me remember. ORAN, Open Radio Access Network Standard for 5G. It's a new thing with 5G where anybody can build an ORAN radio and they can sell it to any service provider because it's an open standard. Everybody can build it to suit or build it to the standard. But at any rate, in this system, they wanted to capture RF signals from 3.3 to 4 gigahertz. And in order to protect that band, they designed a really nice microwave filter that sits on in front of that on the A to D to make sure nothing would get in either side of the 3.3 to 4 gigahertz band. And then I helped them with the modeling of how to undersample that. Remember the undersampling idea we've already talked about. Turns out if you undersample that 5 gigasamples per second, then you could do some manipulation, kind of like in that radio receiver example with undersampling that we looked at. Remember the IF sampling? You could capture that, spin it around, and convert it to a complex signal, and so on. So I worked with the microwave network analyzer data that one of the design engineers sent me, and then I incorporated that into a model so that I could see what was happening, because that 5G band is C-band, and the government used to use that a lot. It's not been given over to 5G, but there are other services that use frequencies either side of that. And if you didn't have a nice front-end filter, those could get in when we're downsampling or using undersampling. At any rate, that was just a recent experience I had where the filter had to be reworked a couple of times, and then I kept modeling with a new version of the filter and was satisfied that I could get away with 5 gigasamples per second, which sounds, I don't know what any of you think. Does 5 gigasamples per second sound scary fast? Just imagine standing there and have this data pipe from this converter running at 5 gigasamples of real samples just flying at you like that. You've got to deal with that. So this was on an FPGA. It's called Xilinx's RF SoC, RF system on a chip, and it has, I think it has 5 of those A to Ds on it. This system for 5G is more complex than that because 5G allows for beamforming. So each channel in the ORAN radio does beamforming with, this is where my brain is going to wig out a little bit. I think it's 6, maybe it's 5, maybe it's 4, I don't remember. So it's going to have 5 channels running in parallel, and then there's beam weights applied to each of those that would come from different antenna elements sitting up there on the tower. If you look up behind here, look up on the top of the hill, there are some array antenna panels up there. They're not just, the standard tower looks like this. If you've not been sort of a studying type person, if you look down on the top of the tower, it looks like a triangle, so it looks like a hat, a triangle-shaped hat, and you'll see panels on each side, 2 panels on each side of that triangle. And that's the typical cellular tower. 2 antennas, so you have diversity, very much like what you have in your Wi-Fi in your house, where you'll have 2 little quarter wave dipoles sticking up off the back of your router, right? So that's the way we've done it, but now with 5G there's going to be array panels up there so that it can do beamforming on the users in the cell. If that doesn't sound amazing, because the need for the beamforming changes as the user moves around. So it's very sophisticated, and it's not deployed yet, really. But at any rate, that was something I was helping with. So another in general problem is just the anti-aliasing filter design. How do you go about doing it? So I have a section in the notes that I'm going to skim over and jump over to the Julia notebook where I can animate some of the math. And the idea here was, let's just model the spectrum of the signal. I chose a Butterworth spectral shape for the signal, and then I would take the anti-aliasing filter and try to make this roll off faster. So I'm in this idea. I'm assuming the information in here is harmonics and other things that I don't really care about, kind of like the noise we were just looking at. I just want it to go faster. So I want to cascade this spectrum and say, let's try to make it look more like that. Okay, so I don't know why that selection triangle is now not going to go away, but it's going to stay there for a while. There we go. So that's what the anti-aliasing filter was doing, and this gives you an idea of what we're trying to do. And this was the type of picture I created in a Jupyter notebook for this project I worked on too, except it was a bandpass signal spectrum, but it was still the same idea. I have the signal of interest lies in the middle, and then when we sample it, we have the alias spectra, and of course those go up and down the frequency axis, but it's convenient just to show one on either side so I can get an idea of what is going on here. And here what I'm looking at is, as a result of the anti-aliasing filter, I would like to make the signal spectrum drop below a certain attenuation level. So this could be called a rejection value. I just called it AdB of attenuation. So the effective gain is minus AdB. So I could control that level by the cascading of the filter, which, remember, is going to come along in here. It's going to shape that so that way that AdB level can be brought lower. And that would be a way of rejecting the out-of-band signals and kind of understanding how that worked. So I built up a model in here using Butterworth filters, and I came up with some design equations for the filter order to say what Butterworth filter do we need to cascade our input signal with, which also has a Butterworth spectrum shape, but what does n have to be to get some additional level of rejection. So I hypothesized a case in here where the cutoff frequency naturally of the signal was 350 kilohertz. I want to put the folding frequency at 500 kilohertz, but the signal is only rolls off naturally with its Butterworth spectrum by about 10 dB by the folding frequency. That's pretty unacceptable, right? Anything above fs over 2 is going to fold back in at about 10 dB. So the idea was to then cascade it, and this equation tells you what the filter order needs to be. When I put in all the numbers, it says it needs to be 16.2, and if I was doing a filter design, which I think you learned about in maybe electronics, they're 3205. Remember doing any designs where you come up with the filter order, you always have to round it up to the next higher integer. Remember that? So here it would go up to 17, which is just crazy high order for the anti-aliasing filter. So here I went through and worked with the idea of oversampling. I was supposing I was going to sample at 1 megasample per second, which is why the folding frequency was at 500 kilohertz. So if I oversample by a factor of 4 and want to get a certain stop band attenuation, which was 60 dB in my design, I could get away with just a first order filter. So this would be my system. This is just you know, a different variation on the example from the book where I would choose to oversample at 4 megasamples per second. I'm now just going to show you even some more stuff like that's related to that and animate it and see if it kind of gets your mind thinking. So I put this in a Pluto notebook so I could have controls in it, but I'm just showing you that even though I'm using Julia, I'm going to bring in the package PyCall, and with PyCall I can import scipy.signal, I can import my package sigsys, and just leverage some of that capability. So the first thing is anti-aliasing filter consideration. So this is pretty similar to what we were just looking at. Here I'm not putting a filter in cascade, I've just got one filter in there, but I can control the order of it. And I have a value of rejection that I can select. So if I set this at 60, that's like the floor, and then I can control the cutoff of this spectrum, and the cutoff is controlled right here. So here the cutoff is like a quarter of the sampling frequency. You know, this is the folding frequency here and here, and you can see not too good. How can I resolve that? I could go with a higher order filter though, so I could take my filter order up like we were just seeing, take it up to like 11th or 12th order, and now anything that's going to come underneath 0.5 is going to be down, you know, in this case it looks like it's down 69 dB. Suppose I would like to get 100 dB. That sounds crazy, but with digital audio we have about 100 dB of dynamic range, about 95. We're going to see that just in a few moments. So how could I do that? So I'm going to move this bar down to 100. Just gives you an idea of what you could do. So with the 12th order filter, very unreasonable. I'm still not anywhere as close to 100 dB. How can I get there? I'm going to kick in oversampling. So I'm going to go with a 4x oversampling like we were just talking about. And you can see with 4x oversampling, I'm definitely there. As a matter of fact, I can cut down on the roll-off rate of my spectrum if I keep it at 0.25. A 6th order filter would work if I was willing to modify the cutoff frequency of my spectrum. Like in the problem I was working at, it was wider than this, so that would actually be more like this. But I'm just sort of dialing in a possible number here. So I can do about 0.3 of the sampling rate. And what I would have to do then, since I'm at 4x oversampling, I'd have to come in with the digital domain here and carve these sidebands down with a digital filter. Is this making sense, or is this animation just so cool to me, but it's not connecting with you guys? Does it kind of, are you connecting with it to a certain extent? I mean, I think this is what engineers have to do. This is one of the things we get to do. And what did I want to do when I grew up as an engineer? I wanted to be a design engineer, and that means you're starting with a problem and you get to kind of architect your own design. And these are the types of things you have to trade off, right? You have to look around, and in this case it would be, this is all an analog design. I didn't show you the code behind this, but I start with using the Butterworth filter that's in scipy.signal, and I'm setting it to analog equals true, which means I'm actually using an analog filter prototype in here. And then I'm just simply placing translates around with overlaying plots. I'm doing other things with the bar. And then in this case, if I reveal what I'm doing, there's the code that controls what the sliders are doing. I'm not going to be around here to teach this stuff anymore, but if I was continuing to teach, I'd probably keep trying to move in this direction to try to get you more in that mode where you can do things like this. but maybe you're not excited about it. I don't know. I'm really excited about it because I like to have visuals to explain my ideas. Obviously, you know, if your spectrum is already very band limited to begin with, then you can take your oversampling away, and you can just play some games. Effectively oversampling might just be with no decimation after you get into the system. Just simply say, I'm only going to allow the bandwidth to be that wide, maybe 1/10 of the sampling rate. And then I've more than met my criteria if I assume my spectrum rolls off of my signal very rapidly. So there's lots of different variations on that you have to go through. And getting back to the 5G project, it was my thought that I should be down, I think I was shooting for 80 dB. The head of the project felt that that was reasonable. He didn't feel it was reasonable to allow rejection down to only, say, 60 dB or something. I mean, here's what you'd be facing. Your project would go down the line, the algorithms would start taking the sampled signals, you do some tests with an interfering environment, neighboring signals around, and then the folding action of the aliasing brings those signals in, and then if your receiver stops functioning well because that interference is aliased down inside the passband, then what do? You say, oh, I have to back up, and yeah, you have to redesign something. Sometimes you go that way, though, and I think our tools are heading us in that direction, so we could create those scenarios all in the computer and model it. So I'm also a fan of that, if possible. But these spectra and these knobs are taking an analog design, which means you've got to go back to the microwave circuit designer in the case of the project I was on, and the company had hired a consultant to do that who was an expert in that. He could build a microwave filter, put it in a box, and ship it to the prime contractor, and they could put it on their microwave network analyzer and sweep it and say, yep, you're meeting what we're looking for. So that's what companies tend to do. They get experts in certain areas to build certain critical components. The next thing we're going to look at is quantization, so we're going to jump over to here. The other things in the signal flow, though, are the sample and hold, which is generally a factor in really high-speed A to Ds where you can't convert it instantly. You have to hold it long enough so that the comparators, or whatever the A to D type is, can grab onto it long enough to do the conversion to digital. And if it's a successful approximation converter, then it has to go through a number of clock cycles. But if it's a flash converter, you can do that in one clock cycle. But a flash converter, has anybody ever heard the term flash converter before? What it simply means is that an analog signal hits an array of comparators, and those comparators have a resistive network there, that each one of those comparators is set to fire depending upon what the analog signal is instantaneously. So it instantaneously has enough comparators to represent all the amplitude levels in the signal. And if you're thinking, like, if it's a 12-bit converter, it's going to be 2 to the 12th comparators. And if you're thinking, can we do that? Well, that's the analog IC mixed signal designers that know how to do that stuff. So flash converters are very expensive, but they're pretty much what you have to do if you want to get the conversion done quickly. They still need sample and holds, though. You have to have some circuit that can hold it long enough for the flash to do its job, depending upon the type. The bottom line in our modeling, though, is that holding might be one sample clock, cap T. So we could model that hold circuit as an impulse response of 1 on the interval 0 to T. And then if we're thinking of sampling out over here with our ideal sampler, that will create this stair-step approximation coming through from the analog input out through the zero-order hold. And see what we're talking about with a zero-order hold. We're talking about having this whole interval, cap T, for the converter to say, okay, it's settled, it's at a stable value, we're holding it, for one sample clock period. We'll get the conversion done, and then we'll move on to the next sample, and so on. But if we carry the analysis down here further, you can see the sample and hold helps the converter make its conversion. It does not distort the signal at all, though, because it's just holding the value that it first saw, holding it out while the converter works. So we could consider it as convolving our signal through the impulse response, but in the end, it doesn't change anything. It doesn't cause any distortion on the signal. There are other issues in sample and holds like droop and other things where it might come up and then over time it might drift off because a small capacitor has some leakage and so on. That's not my area though, but I have bumped into it for modeling that. That's part of the specs usually in A to D and D to A components. Why would a capacitor even drain off voltage? Think about our three principal elements that we have in electronics, passive elements. We have resistors, pretty good in terms of being pure resistance. Inductors, not very good because there's always series resistance, right, between the windings and the inductor. Capacitor, it will have what's called the K value, which controls its lossiness too. It still has a resistance that will shunt the capacitor, but it's very high resistance, but still, if it droops anything, it still kind of destroys the ability to get an accurate reading. So I've only had to look at it occasionally throughout my entire career, but there are models, more detailed models. But with the simple model, the bottom line here is ideal sampling can occur. Next step, and this is our random step, or random process modeling step, we have the quantizer inside of here. We hold the signal ideally at an analog value x of n, but we don't represent it as a real number. We're going to represent it as a fixed point number in any A to D. We just can't have infinite precision. So we have to model what the effect of the quantizer is. And then the second step after we quantize is coding. And coding is not really that sophisticated. Coding just says we're going to take the bits that have been set by the sample in the A to D, say it's a flash converter or successful approximation, and it's going to convert those bits to a particular format. The most common format is 2's complement arithmetic, but in converters that you see in your microcontrollers, like some of the devices that you use in your microcontroller lab, are maybe a unipolar A to D. So then they may not use signed arithmetic because they're only quantizing and coding an unsigned number. So they just might use straight binary, unsigned integer, for example. In signal processing, we generally don't do that. We generally work with bipolar converters. Certainly in the lab, it's bipolar. So the coder part I'll deal with separately. It's the quantizer that we care about. So quantization is taking the analog value that's been held by the A to D and representing it as x hat, and that's representing the fact that there's been a quantization operation of taking an analog level and bringing it up to a finite number of levels that the converter can represent. So this is a picture that appears in the book and the notes. This is a uniform quantizer that uses rounding. And the most important step, well, the step that matters to us is thinking of this in 2's complement, not so much offset binary. I think I've got in my notes because that's a very, very old way. It was pretty much gone when I started teaching, but it still is in the book, I believe. 2's complement is the standard. If we do an N16 and C, that's assigned a 2's complement signed integer. So that's the way the bits get set, and the quantizer can be viewed as a stair step. So if this is an 8-bit quantizer, we can see that we can go down as low as -4 stair steps, because 2 to the 8, 8 bits is, no, this is not an 8-bit quantizer, it's a 3-bit quantizer. It's a 3-bit quantizer that has 8 levels. So 3 of the levels, or 4 of the levels, represent the negative values. If we insist upon having a level at 0, which is the most common way to go, then that takes another bit assignment, and then we have 3 leftover levels for the positive values. And this is how signed arithmetic works in C, Python, Julia, MATLAB, so on and so forth. We have 1 less quantization level on the positive side. You kind of remember this, right? 2 to the 15th. If we think about 16-bit integers, we have 16 bits. One of those bits is reserved as the sign bit. So we have 2 to the 15th levels potentially available. 2 to the 15th on the negative side, 2 to the 15th minus 1 on the positive side, because we're going to allocate one of those steps at 0. Remember how that works? So that's where the 32,767 comes from that we were looking at earlier. On the positive side, we can't go above 32,767. Another name for this quantizer is called mid-tread. And does that mean anything to you? If you're in construction, it probably would. When you build a staircase, which I've not done, but I certainly have seen a lot of staircases, what you step on in a staircase is called the tread, right? So if you look at this, this is like the side view of a staircase. So mid-tread means that we're going to have a step at 0. There's other types of quantizers where there is no stair step at 0, and then you would have an equal number of stair steps, positive and negative, but you wouldn't have a representation at 0. And that puts a bias in, and that's generally not talked about so much. It is possible, though. I think in A to Ds you can control that with some register settings sometimes to be able to say, is it going to be mid-tread or mid-rise? That's called mid-rise, by the way, because what it means is that there's no tread at 0. Instead, you're stepping up from just below 0 to above 0. So there's a rise right there at 0. That's a term that people use. Does all this stuff kind of sound believable? Because engineers use terms that don't apply. This is like a construction term, rise and tread. I mean, who would have thought of that? Engineers think about that, because they have diverse backgrounds. So the code words get mapped out, and the mapping is just done with 2's complement. That's sort of the back end part. I'm not really too worried about that. What's important right now to us is that the book always talks about b plus 1 bits. So b bits assigned to get the levels, and that's going to be this equation right here. If the peak value in the quantizer is xm volts, then delta, the step size, is xm over 2 to the b. This is the bit that's used to just set the sign. And that's in the MSB is where the sign bit gets sent with the 2's complement taken into account. So here's the orientation for that. We have the binary point sitting right to the far left with B0, our sign bit, sitting outside of that, and then all the bits to the right of that are the magnitude bits in the word. And if we're wanting to do a 2's complement setup This is how we could convert that back to an amplitude by toggling bits either 0 or 1 in this equation would allow us to represent the values. I do a little example of 2's complement in here, but I suspect you guys do this better than I do because you've taken all your digital logic and got exposed to this maybe 3 years ago. So that may be your excuse. You haven't done this for a while. I don't know. It was certainly something that you saw at one time or another, though. So moving forward, we're going to now put this together and say we're going to have sampling and then quantizing with 3 bits. So this is showing you the ideal in sample and hold is the solid black line on this sinusoid at each sampling instant. And then with quantization, we get the dashed line. So we're getting an error, and that error lies is plus and minus delta over 2, worst case. Well, I won't put that on there. You can see, though, that the error is going to be either it's going to be high or low by at most delta over 2. So we're going to model that quantization error using a additive noise model. So this is the big leap forward. This is where we use the random process ideas. Quantizer takes a signal and it quantizes it deterministically. This happens in your hardware, happens in the A to D. But we're going to model it for analysis purposes as if we were adding just back again. We were adding in an error sequence E of n. And this shows up in set number 5, one of the homework problems. You can do some calculations with this. So we can say E of n is x hat of n minus x of n. Now, it's fictitious to say E of n is a random process, but that's what we're going to do for modeling purposes. We're just going to say we have the ideal signal and we add noise to it, a noise sequence to it, and that noise sequence is going to involve some assumptions. We're going to assume that it's a stationary random process. It's uncorrelated from the signal itself. This is essentially impossible to justify. Why? Because E of n is directly related to x of n, so how can it be uncorrelated? But I'm going to show you some examples where it seems to hold. It's kind of a mysterious thing. We're going to assume it's a white sequence, and we're going to assume that it's uniform over the error range, and that range is plus and minus delta over 2. So we're going to assume that the additive noise model represents approximately the operation of quantization. Why should I care to model it? Well, in the olden days, certainly people didn't want to run computers every time they wanted to study the impact of quantization. They wanted to have an analytical approach that would involve a random process to get a handle on it. Nowadays, with our computer tools, yes, we can just simply whip it out. And I have a function in the scikit DSP COM SIG-sys module called simple quant, simple underscore QUANT, and you'll be playing with that. You'll be playing with it in project number or problem number I think it's 4. Homework set number 5 at any rate. You'll also see it in use on exam 2. You're going to have some problems where we'll be using it in exam 2. And I'm going to demo it to you pretty soon here. So I'd like to get any reactions to this from you. What do you see as good about this, and what worries you? I mean, in hardware, the quantizer is always there. The true thing is what's in the real hardware. But if we're just trying to model it, we're saying, let's have a generic system model where we can represent the impact of quantization is just adding noise to our signal. That's probably what I'm most interested in your reaction to. We didn't have noise, but now we do because we're trying to represent quantization as a noise sequence. So as a new person to this, you might say, I don't want to go there because I don't think I have to go there. But I'm saying my argument would be, for convenience, we're going to try to model it as an additive noise sequence, because that we can do using linear signal modeling. As soon as we put that quantizer in line with our signal path, it's no longer linear. You see that? That's the big kicker there. If we put this lower approximation model in, that is linear, because we're just taking one path with the desired signal that comes through to the output, and then we modify it by adding an error signal onto it, representing the action of the quantization. So we can use all our linear systems modeling techniques. I don't think there's anybody in the signals and systems group, which is now me, Dr. Tromboli, and Dr. Platt, that would say they want to abandon linear systems models just haphazardly because we want to hold on to them to have the convenience and the ease of doing certain things with them. Where all three of us are huge fans of that because we're systems people. Systems people work at a higher level. We don't want to always be down into the dirt level because we can't really see anything big happening. We need to sit up higher to model this from the systems point of view. Go down there if you need to, but stay up higher so you can get the bigger picture and design systems. I'm giving you a philosophical statement about why I like signals and systems is because I like being at the high level, but I like being able to go down as needed. So I was an analog circuit designer originally, board level designer, and then didn't study DSP until I was getting my doctorate. And now it's changed my life drastically because now everything I do is that, and that's pretty much what happens in industry too. It's changed. The paradigms are changed. If you really like analog though, the good news is there's a job for you because they need analog designers just the same for IC design. Okay, so I say difficult to justify, but so we'll do some modeling here. So this is the uniform PDF, and I'm just restating some things, but what's in this figure, when I was creating my model I'm going to show you in Julia, I went back to this page in my notes to pull out the facts, kind of like, how does this go if I know XM is the peak value of my quantizer. The quantizer we're going to be talking about is always going to be unipolar, so it's going to be able to take a signal of plus amplitude plus and minus XM. So that's like the peak dynamic range on our converter. And then if we say we have B plus 1 total bits, so in my modeling function, simple quant, you enter into it B total, but that's equivalent to B plus 1 here in the notes. So delta is XM over 2 to the minus B, which was on the previous page over here. I think. I guess it just showed up here for the first time. And then we're going to make this uniformly distributed. So what I did here, this example here in the notes was done in MATLAB years ago. Example in Python really wouldn't look any different than this, except I now have simple quant, which takes care of this, but I'm just going to show you the picture. So I generated a cosine wave at amplitude 0.9. I then went through a rounding operation to represent the quantization. I also went through, let's see, the rounding was just for scaling. I'm not sure why I did that here, because in Python I don't do it that way anymore. But I formed the error signal E3, and then I go over to here and look at what's going on with that. So I have the quantized signal, this is 3 bits, The exact is running in the background through a dashed line. And these were old MATLAB plots, which I think are pretty inferior to Matplotlib's quality, but MATLAB's graphics got better too. But there's the error sequence, which has a peak value of delta over 2. And then I increased from 3 bits to 4 bits. It looks more random-like, but it's still, you can still see the periodicity of the sinusoid. As I increase the number of bits in the quantizer, though, you notice that it does pretty quickly start looking like a uniform distribution. So it looks more and more like, at least for the sinusoid, it's uniformly distributed. Is it independent of the input sequence? No, it's dependent on it, but still, this is trying to justify the utility of this model. And I'm gonna do some more looking at that in the tools here in a second, but I want to move on to the last equation here, and this is just coming up with a figure of merit. So the figure of merit, when you have quantization present and you're using this model, is signal to quantization noise ratio. So it's going to be the variance of the signal as if it were a real signal, random or deterministic. So you don't get hung up on this right away. If we're just putting in a sinusoid of amplitude A, what is going to be the variance of that signal? You have to traipse yourself back in time. What's the power of that signal if it's in a 1 ohm system? Over 2 for a sinusoid. So don't fret over this when you see this in homework or in the take-home exam later. It'll be A squared over 2 is the power. Is that good? How could I also get to that? If I took a cosine wave and said it's a random process, I could let the phase be uniformly distributed of the cosine wave on 0 to 2 pi, and then I could take and find the statistical variance of that, and I would get A squared over 2. And I bet you did that you formed a random variable out of a cosine and put a random phase in it, and then you found the variance. Yes? No? Do you remember doing that? It'd be A squared over 2, though. So the equation works out like this. If you dive into the pieces, B is the number of sign bits. So you get a 6 dB increase in signal to quantization noise ratio for every bit of increase in the quantizer. There's a constant that comes out of that, and if you want to get an idea of where that comes from, there's a 12 in there because there's delta squared over 12 for the variance on the sigma sub E squared. And then we're doing 10 log base 10 of that, so that's where 10.8 comes from. And then subtract 20 log base 10 of x max over sigma x. In this term, that reduces the signal to quantization noise ratio. And what does that mean? Well, it's telling us that if we don't match our signal, which is related to standard deviation sigma x, to the quantization dynamic range of the A to D, we're going to suffer a penalty. If we can make sigma x equal x max, we get nothing, no penalty at all. That's going to be impossible, but there has to be some price to be paid. And you've probably seen this maybe in a digital scope or something, where, have you ever seen the quantization in the scope front end? Actually, if you don't adjust the attenuator, it'll be like you're putting a tiny signal into a quantizer that's set to span this range. So your signal is right in here, and it's not getting very many levels to represent it. This was the big argument that the high fidelity enthusiasts had for compact disc digital audio in the very beginning. They said, orchestra is playing, it's going through a really quiet section, and we have this fixed dynamic range in our quantizer. We have these instruments that are really quiet. Now we're going to have a lot more quantization noise effectively on that weaker signal. Nothing you can do about it, and they were not happy. You know, phonograph records were analog, and they had this rumble that would go just from the disc spinning, and so there was some noise that went with that, but they were willing to accept that. They weren't willing to accept, you know, the fact that during a quiet passage you wouldn't get all your 16 bits applied on the compact disc. You'd maybe only get 10 bits or something. I mean, I'm just telling you stuff that I read about years and years ago. It's interesting though, right?
Well, if you do like I know Adobe Audition has a bunch of audio noise removal techniques, and I know from experience it's very difficult in quiet sections.
Right.
Because it's the same thing. It's just there's much less data to compare it. Useful data.
Yeah. And if you modify the dynamic range on the fly using a compressor, then you're taking away the dynamic range of the music, and that's for somebody that wants to hear loud and soft passages as loud and soft, that's no good either. If you're going to a baseball game, I always use this as an example, and the announcer is talking and then turns his head to talk to his companion, the compressor will rise his gain up just so that he comes through at about the same volume. You might, what you hear at a baseball game though, you'll hear the crowd noise come up in the background because they've driven the gain up. Kaylee, remember the AGC amplifier problem in real-time DSP, brings up the background, but the speaker is still at the same level. But for music, that would be totally unacceptable. The quiet passage would not be quiet anymore. It would be gained up, and then you would hear more background noise maybe too. It's interesting stuff for sure. So I did an example down here where I said suppose the signal is Gaussian with a standard deviation of sigma x. If I was to rewrite this, I would probably go with the more standard form that would be 0 sigma x squared. I don't know why I did that in my notes, but at any rate, I said we're going to set x max to 3 sigma to make sure we rarely, if ever, will exceed the threshold, which would create a lot of quantization noise because it would create a massive amount of error when we hit the floor or the ceiling. So that probability of exceeding plus and minus 3 sigma is 2.7 times 10 to the minus 3, so 0.27% of the time. So under this condition, if I go through that equation, I get, say, for a 16-bit converter, which has 15 sine bits, I get 91.3 dB of dynamic range. And I think if an ideal model where you just say a sinusoid is going in, you can get 95 dB. And I think compact disc digital audio was claiming those types of numbers when it first came out, that you would have close to 100 dB of dynamic range with a 16-bit converter. So let's go over and see how that pans out. I do have some quantization noise examples. So for starters, I'm just going to say, because I used this function in Julia just now, simple quant is now called differently because it got renamed to simple lowercase quant down in here, underscore Q. Tronth made that change. I just didn't change this notebook. But what simple quant does, I just put in here what the options are. You get to put your signal in. You get to put in B total, which is going to be like B plus 1. You get to put in X max, which is your peak dynamic range. And then you get to decide what do you want this quantizer to do if you overflow. Will you saturate? In other words, just hold at the max or min negative value? So that's what sat does. If you put in overflow, it will do 2's complement overflow. And what does 2's complement do? If you hit the ceiling, it wraps it around to the negative value. That's very disastrous. Or you can just say none, which means it will just pass the value through without doing anything to it. It's just, this is just a linear, this is just a signal processing block. It's not linear though. So we will take a look at that here over in Julia, just because I wanted to put some sliders on it. So over here, what I created in Julia is I set up a system that's going to put up a cosine sequence. I just named n quant as just the index, because Pluto is very frustrating compared to the way Jupyter Lab works. Jupyter, you get to reuse variables all the time. Pluto doesn't let you reuse variables. It complains at you because it will update every cell when you make a change to another cell, and as long as the variables are distinct, it works beautifully. I put in a phase in here, theta sigma, and then I defined the quantization levels to be x max over 2 to the q bits minus 1, because that's b then. Q bits minus 1 is b, because I'm putting in bits total. And then I'm going to define a quantization noise sequence like we were just looking at in the notes. RAND is Uniform Random Number Generator in Julia, also in Python, MATLAB, so on. So I subtract 1/2 from that, because normally RAND is 0 to 1, right? So I just shift it over by 1/2, and then I scale it by delta. So now it's going to be swinging between plus and minus delta over 2. I think that's right. Maybe I need to put another 1/2 on here. I'm now getting myself confused. Now that's right, because there's a 1/2 embedded into this. This is going to swing between plus and minus 1/2, and then it will be swinging between plus and minus delta over 2 because of the 1/2 that's already built into this. So then I send it through the quantizer, put in the number of bits. I'm just going to put it in overflow, so it will do 2's complement overflowing. Then I form a spectrum estimate of it. And then I also just create a version of this, which is just the ideal signal, which I called X quant, doesn't have quantization yet, and add additive noise to it. So focusing on this right now, this is just the spectrum of the sinusoid, and I can change the phase. It doesn't do anything. I can definitely move the frequency around, and it will move up and down. And here I can control the number of quantization bits. So now I'm going to add in, turn on the additive noise model, and this is just the theoretical approximation for the quantizer as being an additive noise sequence, uniformly distributed. The only thing that's going to make this go up and down is if I change the number of bits. More bits lowers the noise floor, the quantization noise floor. Less bits comes up higher. These numbers seem really tiny, and that's why in digital audio you generally don't hear the noise unless you're really in a quiet setting. You might be able to hear the noise. We're operating at 16 bits, so if I put 16 in here, we're right down to around the 95 dB, minus 95 dB for the noise floor. Take this back over to 10. Turn that off. There's our quantization noise floor, and I'm going to have to play a game here. Let's see. I'm showing you this because when you do your take-home exam, you're going to be doing a problem that involves something similar to this, not the same, but similar. So I set the frequency to 0.123 relative to a normalized frequency of 1 hertz. And now we're seeing the effect of the real and true quantization. And notice that if I change the phase of the sinusoid, the way my spectral estimator is operating, it actually changes the spectral shape. And that's because the way the spectrum estimator is working, it's breaking the signal up into different chunks and FFTing and forming the magnitude squared and then stacking them or averaging them. and it's called an average periodogram. It's the function I'm using in Julia is called PSD, but it's really doing an FFT. It's using what's called Welch's method with overlaps. I'm going to have you use simple PSD in your take-home just because I want something that's very controllable. But the ideas are very similar, and the details of that you'll get when you do the problem. So don't sweat the details. But what I do want to show you, though, is that if I vary this frequency around, we get something called spurious responses. At that frequency, there appears to be no quantization noise, and it has to do with 0.125 is a subharmonic of the sampling rate. So we don't really see the effect of the quantization in the asynchronous behavior. So our model suffers from a phenomena that is the sampling clock and the signal can be perfectly synchronous with each other. And in a practical setting, that's not the case. The signal comes in from the outside. It's asynchronous with the sampling clock. The sampling clock has a little bit of jitter on it. But what people can do or will do in real systems is they will put a dither on the signal to dither it around just a smaller amount to break up this phenomena that we're seeing right here, this spectral phenomena. You notice, though, that it moves around. Sometimes it looks very noise-like, and other times it hits a frequency like there. That's harmonically a subharmonic of the sampling clock as well. And changing the phase on the sinusoid doesn't really alter that too much, but I'm pointing this out to you to let you know that when you work a problem that involves this sort of simulation, it's in the absence of putting jitter on it or dithering on the signal, you can simulate that by just picking a frequency that makes it look more random-like. So now if I add in the noise model, you'll see that the noise model and the quantization, the real quantization, are very similar in terms of the level. But if you don't pick the right frequency, then the analysis model is having a problem. I mean, the tools that we're using to analyze it. So real-world waveforms won't exhibit all of these behaviors, but still dithering sometimes has got to be applied to a signal to make sure that the quantizer doesn't produce those spurious or outputs or spurious signals. Any comments or questions on that? If you've never seen this before, and I'm not sure that you would have, this should be kind of shocking. It's like, wow, where does that come from? It's just a phenomena that happens, and it's more likely to happen in the simulation scenario because we have perfectly synchronous clocks. If we were to make them asynchronous, which I could do with another function called resample, Faro resample in my Python code, then I could kind of make this go away. But it still can come back to haunt you, so some systems have to have dithering in them depending upon the types of waveforms. In terms of how does this track, if I change the number of bits in the quantizer, it tracks and looks about right. Down at 6 bits, it's still working up and down, kind of tracking. The simulation and the behavior level model with the additive noise are tracking each other fairly well. Good? We're going to take a break now, but I wish everything could be perfect, but it's not, because the world's not perfect either. So our math models do lead us into disasters at times. That's just showing you that there's a histogram function available in Julia, and you can normalize it and do all these other things. This is the quantization noise, so it's down to a very tiny plus and minus delta over 2, so the density height is very large because what? The area of this has to be 1 because it's a PDF. We're going to talk a little bit about D to A after the break, and then we'll quickly zoom into delta sigma. So we're going to be hitting this topic, oversampling and noise shaping, and that is very closely aligned with one of the homework problems. 2.98 from the book is represented in this part of the notes. So it's just having you do a calculation with random processes. Let's take a break though. Looks like I've got some Slack messages coming in. Okay, let's try this again. I'm doing an overlay, a narration, because I did not get the recording. So I'm going to be talking here about hints for problem set number 5. So what I've opened up inside the video screen right now is I've opened up the hints for set number 5, and I'm talking about how you're going to work problem 1. You're going to use linearity of the expectation operator to find both the mean and the variance of random variable z. So you will find the mean on x, the mean on minus 2y, and the mean on 2, and that will form the mean on z. And then to find the variance, you will have to work with the expected value of z minus the mean on z quantity squared, and then when you break that down, you will be able to use, again, linearity, and you will take advantage of the fact that the expected value of x times y is known to be, or x and y are known to be independent, so the expected value of x times y will factor into the product, and that will allow you to make this work out nicely. So I don't know what's coming up next on the video, but as it moves along here, we should be moving on down to some hints for additional sections. So I think I'm talking faster than I was in the classroom, so we'll have to follow along here and see where I go, because I don't have an a priori on this except from my memory. So as the timeline stopped, that's kind of an ongoing question for me. The timeline is still moving. Okay, some more action here. So now I'm talking about making a PDF using the histogram function in Python, and I want you to set density equal to true so that you get the histogram scale to be a true PDF. In this case, it's a PDF from -1/2 to +1/2, and its height should be 1 so that its area is equal to 1. It should seem reasonable. So now we're going to look briefly at 298. 298 is, I'm going to come back to that, I'm remembering now. So I talk about the simple rounding quantizer, which we finished up with before the break, is problem number 3. It's a very straightforward calculation. You're just going to go after SNRQ. So you're going to need to know the variance of the signal is sigma x squared, and that's just a squared over 2 for the sinusoid in this model. And then you can calculate the variance on the quantization noise, knowing how many quantizer steps you have, how many bits you have. To do problem 4, that's an anti-aliasing filter, which we did some more talking on when we got done with this overview, but that is just coming up with a compensating filter that you'll need. Now jumping into 298, this problem I'll be talking about as I go through sigma delta converters, and this problem 298 is exactly the sigma delta converter that we'll talk about here shortly in the regular lecture. You start with having to get the power spectral density, and you get that using this result, which I'm dialing to right now, which says that the power spectral density at the output of a system is the power spectral density at the input times the magnitude squared of the frequency response of the system. And that, I'm making my way there. There it is right there. And the input is white noise, so that will be a constant, say 1, and then you just get the magnitude. Or it'll be a value sigma sub x squared or sigma e squared in the case of the homework problem. And you just have to take the magnitude squared of the frequency response. Now when you move into part B, you have to find the autocorrelation function. And that means you're going to have to do an inverse Fourier transform. It's not a particularly fancy transform. You just have to inverse it using the tables that we've already developed to get that phi yy, or phi, whatever it is in the notation of the homework problem. Then the final part is getting the variance. So you're going to see here in a second when I jump over, I don't remember exactly what I did at this point, but we'll just wait for me to make that move here. I'm just dwelling on getting the power spectral density at the output of the first filter and then of the ideal filter. But now, in part D, I suggest that you sketch that spectrum of the first filter, the difference, backwards difference with the ideal low pass, and then to get the variance, you need to integrate that power spectral density, and I'm dialing back now to where that relationship was written down in the notes. And it's coming up right here at the bottom of the page. It says sigma x would be the integral of the power spectral density normalized by 1 over 2 pi. In the case of this problem, the mean on the process x coming out of the cascade of 2 filters is 0, because the very first filter is a difference, E of n minus E of n minus 1, and that subtracts whatever mean would be present and makes it 0. So that will not be present in your integration result to get the variance. And what I did is I numerically integrated the expression, and then I also did the hand calculation. So that takes care of giving you, clarifying some of the hints for problem number 2 from the book. So now I'm going to proceed to dial into the section of the lecture that we hadn't completed in chapter 4. So I see my cursor is about ready to move it down to where we were, and watch me scroll it by here and just see what I've got. So what we were having to finish covering is talk a little bit more about the chain, A to D, sample and hold, the anti-aliasing filter, and so on. Now we're in the back end, the D to A conversion side. What happens there is we have a reconstruction filter, some sort of realizable low-pass filter. The nominal reconstruction filter is a sinc function, but another aspect of this that I'm showing in this figure is that there's a zero-order hold that's part of the D to A converter. It holds the analog sample that comes out for cap t seconds, so that zero-order hold imposes another bit of filtering action, and that filtering action is has a sinc function frequency response. I'll drop down to that here. I just passed by it. I'm going to come back to it here. I don't remember exactly what all I said in there, but we have a cascade action here, and also quantization noise will come out getting filtered as well. As the signal, the desired signal, we'll see the zero-order hold in this chain that processes the digital back to analog. So the most important step is about to be revealed on the next page as soon as I scroll it down, and that is that you get a sine x over x type response, and I should move to that quickly. In this process of narrating, I'm realizing I say a lot of things because I didn't cut to the chase as soon as I thought I should have. So waiting for me to scroll down here. You can watch the other videos from previous years, and I probably spent more time, and we'll have voice to go with it. Okay, so we should be about ready to move down to the frequency response, where I'm going to draw on this sine x over x. This is the zero order hold magnitude response, and I'm going to make note of the fact that between 0 and pi over t, which is the folding frequency, remember pi over t is the folding frequency in radians per second. If you divide by 2 pi, we get 1 over 2t. So I've highlighted there the fact that there's frequency droop imposed by the zero order hold. So what A to D converters will have in them is an inverse sync function response to peak the output up, and that's what this picture here is showing you, that as part of the D to A, they will have the ability to turn on an inverse sync function. In homework problem number 4, you have a different sort of shape that you have to invert to gain level the output. So you just have to follow the hints that I gave for that problem, and it will be along these lines. It'll be some response that's going to peak the higher frequencies up to gain flatten. This is just the ideal zero order hold that's being dealt with here. This is generally done in the DSP domain, so that in the analog domain you just put a low-pass filter, and then you pre-distort or pre-equalize the analog response so that it becomes flat after the effect of the sync function is taken into account. So I rambled some more at this point. I'm ready to go on to the next topic, and I don't know exactly where I went to next, but we'll stand by as the time passes, and I hopefully will get there. I can see, according to my narration recorder, I've been talking for 11 minutes so far. So don't give up waiting. I just kept talking. I don't know what I was saying at this point. Inverse sync functions are a reality, though, and the fact that the manufacturers incorporate them tells you that it's a well-known problem. So the next topic, after I finally move below, is going to be oversampling and noise shaping. And I began this discussion by saying, what if we wanted to be able to build an A to D, D to A system that used less bits, so the quantizer used less bits, or we had a fixed number of bits that we liked, like in this case we have B plus 1 bits, but we're going to capture an oversampled signal and then attempt to get more bits of resolution. And the motivation that I used in this discussion was, suppose you're measuring the voltage in a circuit with a voltmeter. You know it makes maybe 100 or 1,000 samples per second, somewhere along those lines. I don't remember exactly what the DVMs in our labs do, but you use that averaging because you say it's going to be a better measurement. I'm going to average some noise out. So can we do that in the A to D? So I went through the modeling of it. You can see I used the linear quantizer model there, so I had additive noise getting injected. And then I go down here and show the spectrum at that point, which is showing you the desired signal, and then it's going to show what it looks like in the discrete time domain. That's the spectrum to the right. And then finally I'm going to drop down into what happens when we go through the oversampling system. In other words, sample at a higher rate, attempt to get more samples per second, knowing that we're oversampling, but we're going to be able to average and get some quantization noise reduction by averaging. So effectively increase the number of bits in the A to D and or D to A, because this idea works in both directions. So again, I don't know all I was saying. It was early this morning, and now it's about 6 p.m. So we'll see what happens next. As soon as I scroll. Soon I'll be pausing for dinner, and then I'll come back and do some more recording, probably after a rehearsal tonight. So I'm just moving to this picture. So this shows you a spectrum. Notice the gray area is the quantization noise, sigma sub e squared. The signal is oversampled, but if I downsample by a factor of m, what happens is the noise effectively is spread over a different interval, and in fact the noise gets reduced when I downsample. So it gets spread thinner, so I have less quantization noise on the interval minus pi to plus pi as a result of this oversampling. And then I go on to look at signal to quantization noise ratio and make this observation that every doubling of m, the oversampling factor, increases the effective number of bits by 1/2 bit. If you remember, for the linear quantizer, we get about 6 dB per bit. So every time we add 1 bit to the quantizer, we get a signal to quantization noise ratio improvement of 6 dB. Here it's saying that if we also double the sampling rate by a factor of 2, we'll get an additional 1/2 bit of signal to quantization noise ratio. This is just kind of motivating why the sigma delta is such a great idea. Just simply the fact that if you take more samples per second, more than what Nyquist says, you can get some averaging action and you can improve the effective number of bits used in the quantizer. So here's the raw statement, and then in the next line here I'm saying if we wanted to go from a 10-bit to 16-bit using oversampling, we would have to oversample by 2 to the 12th just to get 6 more bits of improvement, and that is ridiculous. So this is not going to get you very many additional bits, effective bits. But this next idea, the delta sigma, does do that. It has this feedback loop with an integrator, which is the same as sigma. Sigma is a discrete integrator. And then an A to D converter, and then a feedback path through a D to A. And the delta part is the difference between the input and the fed back signal from the D to A. That's what's going on there. This is a mixed signal circuit. There's switch capacitor integrators, and then there's digital portions that do DSP sorts of things in this type of A to D, and also D to A. So if we create a linear noise model from this, we first draw the discrete time model, which has the 1 over 1 minus e to the minus 1 for the integrator, and then next to that is the quantizer that would be representing our A to D. And then we feed back through a z to the minus 1 to make sure we're doing things in a causal fashion. We can't send the input back without having at least one sample of delay in it. So the next, and then of course the system is followed up by a low-pass filter for anti-aliasing before we downsample by M. Okay, so we create a linear noise model of this. We replace the quantizer by a through path, and then have an injection of quantization noise error E of n, which we talked about before the break. That's the error between the unquantized signal and the quantized signal. So we're going to inject quantization noise. This block diagram is exactly what you analyzed in an earlier homework problem where you did a feedback analysis and initially had generic H1 and H2 in the block diagram. Here it's Hx, the effective transfer function, and Hz or He. But when we develop that model, we can redraw the feedback model to look like this. We have the input going straight through, hitting the low-pass filter and the downsampler, but then we have our quantization noise gets fed through a backwards difference. So we have 1 minus e to the minus 1, which is like a differentiator. And this, by the way, is exactly what you're modeling in homework problem 298. Homework problem 298, as I'll draw on this momentarily, is just E of n going through the block 1 minus e to the minus 1, and then going through the ideal low-pass filter.
That was my guess.
So the input is shut off. That homework problem just focuses on what is the noise coming out of the low-pass filter. It doesn't even include the downsampler, as I'm recalling it. So that homework problem is very similar to this delta sigma modeling, and what we're going to see here shortly is what the modeling looks like. I'm skipping a lot of the detailed math, but I'm just covering the top level of all of this. So this is relevant to what you do in problem 298. It's not the exact same notation, but the idea is you start out finding the spectrum after the filter, and that's that capital phi, and there's the result. And then you want to find the noise power contained in that, so we integrate the spectrum. So that stuff I just zoomed over is related very closely to problem 298. Now we're just looking at the benefits of the noise shaping. The action of the sigma delta is to shape the noise spectrum, so rather than it being flat, white noise in the spectrum of interest, or in the band of interest, it's going to be shaped so that it goes down to 0 at 0 frequency and then rises back up. And this gives us a performance improvement. We're able to get more bits of effective, more effective bits added to our quantizing operation, or A to D. In reality, what people are shooting for with this idea, the sigma delta, they want the quantizer in hardware to be just 1 bit. So they want to build a 1-bit A to D and use oversampling with noise shaping to get multiple bits of resolution. In the beginning, with this technology, they were looking to get 16 bits. So here's zooming in and doing some more detailed analysis. And then I finally write it down in terms of delta B, or delta B1. And this is just comparing different strategies. With noise shaping, you can see you get considerably more bits added. Say if you 64 times oversample, you get an effective increase in bit width of about 8. If you're just doing this using direct oversampling without the shaping, it's only 3.5. So this was a great discovery that was made. It doesn't go far enough though, so going to a higher order noise shaping is typical in devices like what the FM4 board uses. So here's a second order noise shaping, and then you see the effective transfer function in the linear noise model is a cascade of 1 minus e to the minus 1. So it's 1 minus e to the minus 1 quantity squared. So that's a more drastic shape to the noise from the delta sigma by having 2 integrators in it. Go through the model, and now we just sort of extrapolate from there to any order quantize, any order, any number of integrators. So P is the number of integrators. So you look down the page here and you can see what we're really targeting is the third order sigma delta, which is the row that has P is equal to 3. And you can see that with 16 or 64 oversampling, 64x oversampling, the increase in signal to quantization noise ratio is 17.45, and if you're using a 1-bit converter, that means you'd be at 18.45 effective bits. So this is wonderful. We were looking initially for 16. You can get 18, and with other variations and other new tricks that have happened over the years, you can now get into the 20s. In other words, 24 bits or higher of effective bit width with the sigma delta idea. So I'm waiting for me to move along here, but I'm probably going to stop and start another session here shortly. So I'm going to wait till it transitions. I think the next thing I talk about is how this same idea applies to D to A converters too. I'm looking at the clock. This was at 10:23 in the morning, so just going to wait. Yeah. So I'm going to stop here. Okay, we're going to get back to this after taking a break in the narration. So I'm going to narrate this last section of chapter 4 where I'm talking about oversampling and A to D conversion. So, or D to A conversion, excuse me. So I'm basically moving very quickly here, just showing you that there's block diagrams that show you the configuration of making a D to A function with noise shaping, just like we did in the A to D. The same principles hold. The delta sigma is used in both ends, and it's very powerful at being able to make a 1-bit converter into a multi-bit converter. So again, this is just showing the spectrum, the noise shape spectrum in the D to A, similar to what we had for the A to D, with the shaping and generally with a higher order set of integrators to form the sigma part of the scheme. So wait to see where I go next, because I don't know what all I said in here. My brain is fading out from this morning on what I did. So just wait for it to move on here. I will be showing an example shortly of what's found inside the FM4 board, for example, or most any of the audio microcontroller boards I have that have dedicated A to Ds and D to As for doing audio signal processing. So I'll show that example here shortly as soon as we move on. So this is showing the pth order shaping factor, which is just the sine function raised to the 2pth power. And of course you analyze that in problem 298 for just p is equal to 1. So I did do a simulation at one point in my life of the delta sigma, and I'm just whizzing past that and showing you that the spectra with the noise shaping was as expected, and then overall when I came out of the downsampler and with the low-pass filter in front of it, I do see the noise floor lower than just oversampling ADC, which is to be expected. So now I'm looking at a couple of different codecs that are out there. The WM8731 is a codec that is used on the FM4 board that we're using in the lab right now. And this just shows you a little bit about its specs. I point out in here that you can do word lengths of 16, 20, 24, and 32-bit words. So with the power of the delta sigma idea, you can get very high precision conversion in the system. Right now in the FM4, though, we're just doing 16-bit signed integer for left and right channels. And the sampling rate is programmable up to 96 kilosamples per second, which is very nice. These are some plots of what, in a normalized frequency axis, what you get with the effect of the oversampling and then the stages of upsampling and downsampling with filters put in between. So you see a nice flat spectrum up to 0.5 hertz, a rapid roll-off, and then you see these other spectral components. Those are just components that arise from the multi-rate processing and not having perfect interpolation or perfect stop band rejection in the downsampling. That's kind of the way things like that work. It's not perfect. That's above our audible hearing range, so it's not really the issue that it might appear to be. Then I develop some continuous time random process results and go through an alternate power spectrum derivation. Just, I felt like doing it. I'm not sure why, but so just a quick image of what's going on in the A to D problem. That was just on the screen, though. It wasn't something I've really talked about. So now I'm jumping into chapter 5, which is what we're going to cover all next week, so we can get that wrapped up for taking the next exam and get the homework problems worked out. I will be putting up a hints page for the set chapter 5 problems very soon. So transform domain analysis of linear time invariant systems is just pulling together all the ideas so far from the class. And you can see some of the key topics that are going to be new that we're going to go through. I'm going to outline those here. So we're going to introduce group delay as kind of a new topic. The Paley-Wiener theorem will get talked about too in a moment. Inverse systems is how we can try to invert an action, and that will be an interesting investigation. Geometric evaluation of h of e to the j omega. The inverse systems idea is going to show up on the next exam, actually, so I'll probably highlight that when I go cover it next week. All path systems are particularly interesting in how they relate to magnitude and phase. You can hide systems inside of other systems with all-pass filters. Generalized linear phase will kind of cap off the chapter, and it's how we display the power of FIR filters with linear phase in signals and systems. Those of you in the lab have already used linear phase FIRs in lab 4. You've also used linear phase FIR in project 1, problem number 2, where you have the interpolation filter that's designed with FIR1 from SciPy.signal. So I'm about ready to move into the kickoff of the chapter. And the kickoff is just a quick review of back in chapter 2. We started with time domain, where we have the convolution sum to get the output from the input and the impulse response. And then we have, latter half of chapter 2, we have the Fourier transform as a means of doing it in the frequency domain, multiplying the frequency response times the input spectrum to get the output spectrum. And then in chapter 3 with the Z transform, we work through the same idea using Z transforms. All those techniques are now kind of at our disposal, and they're very significant things to be able to do. So frequency response of LTI systems, this is kind of some material to expand upon what we've already done. We're not just talking in general terms, we're talking now in more specific terms. So here I'm showing what are the 4 types of ideal filters that we use sort of as a prototype or a objective. We can't build these filters, but we can get close to them. So we have the low pass, the band stop, and then in the second row the high pass and the band pass. And at this point in the lecture, I went and opened up the textbook to a problem that I've assigned in set number 5 that is a very nice problem to show you how you can approximate these 4 filter types using just a low-pass filter and using a combination of complex frequency shifting and up and down sampling. So that problem, I don't have my book in my hands right now like I did in lecture this morning, but I flipped open to that page. It's about the 4th problem in the assignment. I'm thinking right now it's got A through E parts. You have to just analyze these different configurations and see what type of filter they're building. low pass, band stop, band pass, or high pass. It's a fun little problem, and then I suggest doing simulations on it in Python to just kind of validate the ideas. I'll probably be hinting some more at that next Wednesday in class, and you'll see some discussion in the hints page too. So let's see if I talked long enough for me to move on from this, because this is when I had moved away from the bench, and guess what? I was untethered at that point, so I got over to the table where I keep my book, and it never dawned on me that I wasn't plugged in, of course. So I think we're going to move on from there, from that discussion, and now we're going to talk about what limits us from getting to this idealized filter, and that's the Paley-Wiener theorem. We know that the ideal filters will have impulse responses that will extend from minus to plus infinity, which makes them computationally unrealizable. So what can we hope to get? And this theorem is a nice result. It's kind of abstract. I'm just giving it to you in face value. It says if h of n has finite energy, which means it's absolutely summed, can be summable in the squared sense. So the sum of h squared of n is finite. And if h of n is 0, for n less than 0, meaning it's causal, these are properties that help us understand stability and causality. This integral will be less than infinity. And the first thing you can notice from this integral is that you've got log of a magnitude and then the magnitude of that integrated. So the first bullet point there says if you have isolated points in the frequency response plot that go to 0 to define a stop band, that's acceptable. You can handle that in the integration. You can have an isolated point that goes to 0, and the log of that would be minus infinity, and then the absolute value of that would be plus infinity. That won't destroy the ability from a Riemann sum sense, which is our approximation to an integral. But if you have a whole band of frequencies, a finite band that you're trying to set equal to 0, like an ideal stop band, you cannot do that because you'll have the log of 0 over an interval, which will be minus infinity and then plus infinity integrated, and that will not be less than infinity. So can't make that work. So what can we do? So the next lower part of this page here is going to kind of look at what the Paley-Wiener theorem limits in the design of a realizable digital filter, or analog filter for that matter. I'm sure I said more than I just said now, but I have no idea when I'm going to shift down, so I'm just going to kind of hang out here, wait for me to move down the page. If you're watching this for the first time, understand that I'm just narrating over the top of the video that did not have audio recorded. So I sidetracked for a long time on this, I guess, because I'm now just highlighting the section that I've already talked about. Okay, so now finally moving down the page, what is possible? So this shows you a generic low-pass response showing that we can accept ripple in the pass band, and then we can have ripple in the stop band as long as we just have isolated points of ripple in the stop band where we can touch 0 for the amplitude response to the filter. And then, of course, we're interested in adjusting the transition band, and generally in a filter design, the transition band is something you try to make as narrow as possible, but you find that the order of the filter goes up very, very rapidly when you make that transition band narrow. Elliptic IIR filters are known for having the narrowest of all filter types for a given order to get a narrow transition band. Talked about that in lab today after class because we were looking at lab 5, which is on real-time implementation of IIR filters. So this is like a generic response, a wish list. So the next topic here is phase distortion and group delay. This is partially a new topic. If you took Com 1, you would have seen group delay already in that class. And probably in EMAG, Dr. Song may talk about group delay at some point too. We're all talking about the same concept though in group delay. So first of all, phase, linear phase. If we have an ideal delay system, like an impulse shifted by ND samples, the frequency response of that system is magnitude 1, and the phase shift is linear in frequency. Another idea is the ideal low-pass filter. If we put in that e to the minus j omega nd in the pass band, saying we'll tolerate some delay, we can come up with the inverse Fourier transform of that as being a sinc function. And I wrote something down here. It should say just over a band of this interest, not just of a band of interest. Just over a band of interest. So the linear phase idea is just in the band of interest, the signals we care about, we want to have at most linear phase. So this sinc function designs us an ideal low-pass filter that has ND samples of delay, but unfortunately it still requires N to run from minus to plus infinity. There's no way we can shift that to the right far enough to not have the tails of the sinc function active, making it a non-causal filter. But it will be linear phase, just we can't build that. So now we're going to move on, and this is very close to the end of the lecture now, about a minute or two left, the concept of group delay. And I'm going to zoom over this and show you a neat example at the end of the class here, but this is showing you, suppose we have a signal S of n that we're going to multiply by cosine. So this is like the modulation theorem and Fourier transform. So we have a narrowband signal that we shift up about a center frequency omega naught, and we're going to try to understand what it means to have group delay by using the definition and then considering this. I'll revisit this next week, but group delay is minus the derivative of the phase response of a filter. And if that group delay is constant, that's what we're interested in. That means all frequencies in a narrow band, say the bandwidth of S of n, up at the top of the page there, if they receive the same group delay, that means there's no dispersion, which means everything's cool. There's a linear phase in that pass band to give a constant group delay. So here, in this final example, I just look at something that's now in our textbook, but I incorporated that in my notes early on. Two narrowband signals, pulse signals, going through a low-pass filter. And here's the spectrum of the pulses. They occupy two different frequency bands. They both lie in the pass band of this low-pass filter that has equal ripple pass band and an equal ripple in the stop band. But I can do something inside this filter that you cannot see in the amplitude response of the filter. I can introduce non-constant group delay by using some all-pass filters. We'll learn about that a little bit later. So in the bandwidth of the first signal spectrum, I've pumped the group delay up to 100 samples. And so what this does that's really intriguing is these signals arrive at the input at two different times, x1 first followed by x2. But x2 or x1 arrives first, but it hits the large group delay of the filter, and it comes out after x2 does. It's a very intriguing thing. This is a realizable filter. It's just showing you that group delay can take a band of frequencies and make one signal come out later than the other one. So it's like when the signals go through the filter, one passes the other one. kind of an interesting concept. It's true though, and I can demo that in a Jupyter Lab notebook. And I believe this is the end of the lecture. I think I've wrapped up here and shut everything down. Don't know what screen was showing when I shut down, but I'm willing to bet at any moment here I'm going to shut the system down. So we'll come back and look at this again next week. That's the end of the video, and I'm going to stop narrating. The video may continue, but the audio is going to go away. Okay, hope this comes out okay as I set off to process the video now. Bye.